Do larger butterflies live longer? The wingspan in millimeters and the lifespan in days for the adult state of 22 species of butterfly are listed below. Number 1, compute the least squares regression line for predicting lifespan, y hat, from wingspan, x. So this is to say that the lifespan is the dependent variable and wingspan is the independent variable, as listed in the chart, independent and dependent variable. So we're going to ask GeoGebra to compute the least squares regression line for us. And you can see I've already entered all the data, so we need to highlight them. Highlight the data and ask for a two-variable regression analysis. And we have the following scatter plot. So looking at the scatter plot, it's questionable whether we should be using this as a linear model. It does. It's sort of cloudy. It's a little ambiguous, so we can proceed, but with caution. It's a weak correlation, if anything. And you can see the correlation coefficient is 0.14737. But in any case, to answer the question, the model, the best fit line, the regression line is right here. It's y hat equals, and let me put that in. It's y hat. Where are we? Y hat equals negative 0.8525x plus 51.7712. Let's go back and look. Oh, no. Let's go back and look. Here we go. Negative 0.8525x plus 51.771. 7712. Okay. Good. Number 2, can you conclude that wingspan is useful in predicting lifespan? In other words, are the variables linearly correlated? Well, we've already seen from the scatter plot that there's a weak correlation, if any, and the correlation coefficient R is negative 0.41737. So this is a value for which we need to do the significance test to answer this question for sure. So that's what we need to do. We're going to do the significance test for R. So number 2, we have R equals negative 0.4174174, and the number of observations is 22 because we have 22 species. So so that means we calculate T, the test statistic, as R times the square root of n minus 2 over the square root of 1 minus R squared. And in this case, that's negative 0.4174 times the square root of 20 over the square root of 1 minus negative 0.4174 squared. Okay, so if we ask, we'll put that into the calculator or ask GeoGebra to calculate it for us, we're going to get negative 2.05417. Negative 2.05417. So that's the test statistic, and that means we need to, on the t distribution, this is T20, n minus 2, 0 is here, and negative 2, we'll say it's right about here, negative 2, and so what we're looking for is the area outside the two tails, outside the middle, so in the two tails, and so these tails are symmetric, so we're just going to double the area of one of the tails. And so our p-value is 2 times the t distribution with degrees of freedom 20 and value negative 2.05, and I won't write the whole thing here, it doesn't fit, so let's just call it negative 2.054. And we'll get the p-value from GeoGebra. So back to GeoGebra, we can close that window and then go to the computer algebra 2 times t distribution. Degrees of freedom is 20. Variable value is negative 2.05417. And we get 0.05326. 0.05326. 0.05326. And since we weren't told otherwise, we need to compare that to 0.05. The p-value 0.05326 is greater than 0.05, so we conclude that the variables are not linearly correlated. So the correlation is not significant. It's not significant. Okay, and now number 3. So let's do number 3. Do large butterflies tend to live longer or shorter lives than smaller butterflies? Explain. We can't answer that question. We don't know. So there's no correlation between wingspan and lifespan. So wingspan and lifespan are not correlated. So, well, we can't answer that question. It's neither. The result of our analysis is that lifespan and wingspan are not correlated, or not significantly correlated. So wingspan are not correlated. So the best answer is neither. Big butterflies can live any lifespan, and small butterflies can live any lifespan. There's no correlation between the two.